Hello again, I'm Dr. Bettina Heinz and I will teach you more about chemistry today, hopefully. We will talk about atomic theory number 4 or part 4, which is dealing with some complex topics. Atomic theory is a difficult subject, but it can be handled, but there are a lot of overlaps. So we will see what we'll discuss today. We will learn a lot about spectra, visible, UV, infrared, the Rydberg constant, that is a constant that relates to the energy released when an electron comes from infinity back to its ground state level. And for hydrogen, that would be the first shell, for helium also. But since the atoms are all a little different, the Rydberg constant would be different. The Bohr model, orbital diagrams, quantum numbers, the quantum levels, the Schrödinger equation and the significance of the Schrödinger equation, the sub-energy levels, SPDF orbitals, Pauli exclusion principle, the Hund's rule that relate to degenerate orbitals and their filling procedure, electron configurations, and orbital energy diagram. Now that's a handful. We'll see how well we get and to cover all these topics. Now first I'd like to tell you a little bit about spectra again. Spectra is the diffraction. Spectra result from the diffraction of light through a particular material which is called the prism. It is usually made out of quartz, but refraction can occur everywhere through a raindrop or through your teardrops. So it has to be a special type of shape that allows the light to be split into its components. So polychromatic light will be split into monochromatic sections. Now here we have in this picture a spectrum going from the gamma, the most short wave energy, to the most long wave energy lengths or wavelengths. Gamma radiation is the most powerful. It is very, very short wavelength dimension, but also very high frequency. Then we have X-rays, then UV, and UV can be divided into soft and hard UV. Then we have our little visible segment of the spectrum, the total electromagnetic spectrum. So in a way, we are all peeping toms, you could say. We only see what is found in this particular part of the total electromagnetic spectrum. And when we look at the visible spectrum a little closer, we can see that we go from the UV or the violet to the blue, the green, the yellow, the red, and beyond that we will get the infrared, which is not visible to us anymore. Although I must mention that there are some animals that can see in the infrared, and there are also animals that can see in the UV. Certain goldfish can see in the UV, and snakes can see in the infrared. But that's just an example. There are probably many more animals that have a little shift in the spectrum to which they are sensitive to. We humans, of course, have our little window of visibility, so to speak. So we have infrared, microwaves, radio TV waves, etc., etc. So we have a certain array of different wavelengths that go from short wavelength to long wavelength, or high frequency to low frequency. The product of lambda, which is a symbol for the wavelength, and nu, which is the symbol for frequency, it's a Greek letter, nu, but often we find the F. I can't say F word. I mean the F, small f symbol used for frequency as well. So our visible spectrum goes from about 400 to 800 nanometers. And the wavelength is shown here in the picture. We go from peak to peak, or from trough to trough, or from the beginning of the wave to its full cycle. So you see it's based on the circle. That would make a full wavelength. Wavelength is a distance And frequency is cycles per second, you could say, or waves per time period. So waves per second, any full wave per time period is called a hertz. So waves, 1 cycle per second is the hertz unit. Hertz was also a famous physicist in Germany who studied these phenomena. Now the spectra are divided into different types. We have the continuous spectrum, as we see here on top, which is a rainbow spectrum. All the energies sort of allied into each other. It's like a smear type of spectrum. Then we have the absorption and emission type spectrums or spectra. And we have distinct energy levels here, as you can see in the bottom. We have a black background and the light parts or lines which represent the distinct energy levels of the analyzed substance, which produces light itself. So it's energized enough to produce light itself. And when that is diffracted through a prism, then we get a line spectrum. But in this case, it's called an emission spectrum because the light is emitted. On the other hand, we have an absorption spectrum, which is practically like a negative of the emission spectrum. We have everything reversed. The background is a rainbow array, and the black lines are those areas where usually the emission lines would be. So that means the substance is blocking out that part of the electromagnetic spectrum. Here we see it a little larger. Again, the rainbow spectrum that is a continuous spectrum, continuous emission spectrum, like the sun or an incandescent light bulb produces that. And here we have the emission spectra and the inverse of that, the so-called absorption spectrum. Now, in order to study, or in the early days, the discharge tubes played a very important role, or the cathode ray tubes played an important role in producing light coming from particles like the electrons that are emitted by the cathode ray tube. And here we have an image of the cathode ray tube with the two electrodes, the cathode here on the left and the anode on the right with a power source. And these tubes are semi-evacuated and filled with a certain material. And the earliest material that was studied was hydrogen gas, because hydrogen is a very simple atom with just one electron system involved. So it's the most pure type of physical model to study different wavelengths emitted by this light that is produced by the recombination of the electrons with the residual ions that are produced during the bombardment with the extremely fast electrons coming from the cathode. That's why they are called cathode rays. This light, if we send it through a spectrum, will give a very distinct line spectrum. And I try to picture that here for you. The lines are at first wide apart and then get closer and closer together, similar to a logarithmic type of scale. And this would be visible. So if we project the light diffracted by the prism onto a screen, then we can see a beautiful spectrum. The series produced are as follows. We have the Balmer series from the end of the 19th century. This was mainly investigated. And you can imagine that the visible spectrum was the earliest that was investigated. And because it was visible, you didn't need extra instruments to recognize what was being produced. So the Balmer series is that spectrum that we see here right in the picture. That means later on we are jumping a little bit to a conclusion, but it means that all the electrons that are propelled to higher energy levels are falling back to the second shell. So the light is produced when the electrons fall back down the staircase of the electron shell system. And then that electromagnetic energy is given off to the environment, and we can measure it then with the help of physical methods. So the visible part of the spectrum represents what we call the Balmer series, because Balmer was the first to analyze this. Then later on, other scientists worked on various hydrogen spectra. Some of the spectra were produced in the UV section of the electromagnetic spectrum, so that wasn't visible to the naked eye anymore. You needed a special UV detector for that. Later on, it was determined that all these transitions go back to the first shell, so the innermost shell. So electrons coming from higher energy levels go back to the first shell, and that gives off UV light. The spectrum is going to be very similar, only a little bit more contracted, but not any visible colorful lines. The Paschen, Brackett, and Pfund series all have to do with infrared spectra. That means the electrons are going to energy levels that are beyond the second shell. So each shell that is the landing site in the final state has its own particular spectrum. Like when we go back to the third shell from higher shells, then we call that the Paschen spectrum. Here the infrared are the same pattern again, only much more extended. So the UV are very short, narrow. The invisible is maybe like this, and the infrared are really spread out. But the pattern of the lines is the same. Only, as I said, not colorful lines like in the visible. So these are infrared spectra. Of course, there are more energy levels. That's why we have more infrared. Now, I'd like to show you some of these discharge tubes that we use in the classroom. Simple cathode ray tubes that have different filler gases like hydrogen, neon, mercury vapor, helium, and air. And I will show you now a lab video that also goes into more detail, and also will show you the types of discharge tubes that were used in the days where these tremendous experiments were made that revolutionized chemistry. Here goes. Hello, we are back in the laboratory. Today we will talk about nothing wet but dry. We are dealing with discharge tubes, so-called cathode ray tubes. And the rays that are being produced in these tubes are coming from gases. So they are also called gas discharge tubes. And we have a variety of tubes that are filled with various gases. For instance, here on the left we have helium. We also have neon, but we don't have enough devices. So I have to wait and let you watch this first, and then I'll exchange it with neon. So helium has a wonderful orange color, but neon has that beautiful bright orange-red neon color to it that you will see soon. And this is hydrogen gas in this tube. Here we have mercury vapor, nice blue color. And here our wonderful air that is a mixture of gases. Remember, it's nitrogen, oxygen, CO2, and noble gases, mainly, of course, nitrogen and oxygen. The discharge tubes, and I'm going to turn this one off so I can replace it then later with the neon tube. But I want to show you how it looks. We have here neon. That means I can know that this is neon and not something else. We have an evacuated glass tube and two electrodes, one with the, which is called the cathode, meaning the electron emitting cathode electrode, and the other one is the anode, which sucks up the electrons. So it is the electron receiver or acceptor, and the cathode is the electron donor. So when we insert it in within two electrical poles, provide an electrical current, then the electrons will step out of the metal cathode material and will be accelerated across this path to be attracted by the anode. As the electrons are accelerated across this distance, they will collide with the filler gas, which is neon in this case, and they will ionize the neon atoms. That means knock off electrons as they bump into these atoms, and these stray electrons will eventually reunite with the ions, and as they do that, they will fall down the staircase of the electron shell system to the appropriate energy level that will make the electromagnetic radiation visible to us. that means they come back to the second shell. And this will be visible to us human beings. Some animals can see infrared, some animals can see UV, but we call it visible when we can see it. I guess this helium tube is cold enough for me to take it out, because they get pretty hot. So every transaction produces a lot of heat. And I'm going to turn it on again and look, the beautiful orange. The blue and the orange give a wonderful color combinations for your neon sign that you have in mind. So you see here we have a variety of different discharge tubes. I want to show you quickly some old-fashioned tubes that were used to elucidate the structure of the atom, the fundamental particles that were made visible by these modified discharge tubes. This is a special one that allows the shadow formation by virtue of cathode ray emission. And we have all shapes and sizes to produce different things. For instance, X-ray tubes and these so-called canal ray tubes, which are the positively charged rays produced. Cathode rays are negatively charged rays, meaning electrons. Here in the back, we see not a discharge tube, it's just a glowing wire, which produces a continuous spectrum, just like our light bulbs. It's tungsten wire, and it's heated up so it produces not a red hot glow, but a white hot glow. So tungsten has the highest, one of the highest melting points, about 3,000 degrees centigrade. If we take a spectroscope and we look through it, when we look outside, we see the wonderful rainbow colors. So this spectroscope will diffract the radiation into its parts. And the sunlight, and as well as a light bulb, like an incandescent light bulb, will produce a continuous smear of the spectral colors of the visible part of our spectrum. These will produce a line spectrum called an emission spectrum. So we see beautiful bright colored lines that make up this particular light, like a red band or a blue band and a green band or a yellow band. So every gas has its particular character of spectral lines. If it is a glowing material, it produces distinct line spectra, not continuous spectra, but distinct line spectra, which we call emission. If this gas is between the sun and my eye, then we see darkened out areas where usually the lines would be in the emission spectrum. So it's like a negative spectrum with a continuous background spectrum. So I hope this was interesting for you. See you next time. Yes, I hope that was interesting. Let's look at the discussion here again that we just had about the spectra. We have here the continuous spectrum. So I'm showing you practically the same again, only you can see here the glowing body, like a heavenly body, like the sun or a star. We use a slit to narrow down the light, send it through a prism, and project it onto the screen. We have a continuous spectrum. Below here, we have what we call an absorption spectrum. That means some material is between the light source and the detector mechanism, which is our prism and our graph, or our screen. So the sun radiates as usual, but the particles in between will take the energy that they need for their own energy transitions, electron transitions, practically cutting out the segments out of the continuous sun spectrum and using it to propel the electrons to higher energy levels. That's why we call that absorption. Now, these segments will then be missing from the continuous array of the rainbow spectrum, which is the light-producing sun. And we call that a line spectrum. Remember, black lines on a colorful background. Then on the bottom here, we have the emission spectrum. So we roughly indicate here that a material is excited that much that it's at a very high energy state, which has enough activation energy to bring the electrons to higher energy levels to propel them upward. And when they fall back down, they give off the electromagnetic radiation, as we have already discussed extensively. So the material produces its own light, which can be diffracted by a prism. And then when we observe it, we have bright lines on a white background or dark background, excuse me. So I would like to show you another little lab video which relates to what we call flame testing. That means we excite usually alkaline metals, and they produce all their very interesting monochromatic light. But when we diffract it, we get also various colored lines in our spectral array. So I'd like to show you another interesting lab video that has to do with flame tests. So enjoy, please. Well, welcome back again to our laboratory session, to another exciting experiment. Today we will do the flame tests of alkaline and earth alkaline metal salts. These metals in the ionic form will produce wonderful colors when they are excited by a flame. That means the electrons make transitions and fall back to their home base, so to speak, to their original energy levels, and give off electromagnetic radiation, which are made up of certain wavelengths, which lead to certain colors, of course. With the help of a little spectroscope, we can diffract that light and see particularly lines in a so-called emission spectrum. Now, this is how we work this. We will use a little petri dish. There are different ways of making flame tests, but this is quite handy. We use a petri dish, specially designed for this type of flame setup. We use a solution, so I'm going to use lithium chloride. Lithium will be our first test. But the setup is as such that we will prepare some hydrogen gas with the help of mossy zinc and hydrochloric acid. So I'm going to put into this petri dish some mossy zinc. And that is a single displacement reaction, as you remember, with HCl. And that's always a ready way of making hydrogen gas. Hydrogen gas generating reaction. So I'm going to pour a little 6 molar HCl on top. And you already see the vapors coming out. And then I will add my lithium chloride solution. Oops. Make sure it doesn't overflow. Put the lid on and then slide this. Oh, you can see already how this color of the flame is turned into a beautiful rose-like red, you could say. So it has some magenta tones in it. Calcium would be a more brick red type of color. Lithium makes a beautiful red, a candy red type color. Strontium is also of this category, makes a beautiful pink, intensive pink color. Barium makes a green color. Sodium, we all know from the sodium vapor lamps in parking lots, and especially here in San Diego, to prevent the big telescope on Palomar Mountain to be contaminated with regular street lamps that are not of the sodium vapor type. So it has a certain significance in our area, the sodium vapor lamps. I'm going to make some fireworks here. Well, something that they use for fireworks as well as for sparklers. Like on Christmas trees, some countries put sparklers on the tree and then ignite them to make these nice little harmless sparkles. So little stars. Ooh, something popped here. And I could keep that up, but we have our time limit, so we can't entertain you forever with this. But we will try another salt solution, the calcium chloride, the next time to see how it contrasts to this color. Now, wasn't that interesting? A beautiful colors produced by these glowing alkaline metals and earth alkaline metals. They're very good because they have just one valence electron or two valence electrons, so they're easy to excite. Now, talking about iron, remember I made that nice little sparkle fireworks presentation for you. I'd like to talk about Planck's experiment, the famous German scientist named Max Planck, who was born in the same city as I was, Kiel, Germany, northern Germany. So here I'd like to talk a little bit about Planck's black body experiment. He used an iron block, the same material that I used for those sparkle effects. Those were iron filings. Here we have an iron block. This is a very simplified way of showing this experiment. We have an iron block, and when you heat it up before or below 750 degrees centigrade, it behaves as a black body. That means it doesn't radiate anything. It absorbs all the energy but doesn't give off any radiation. That's what we call a black body. Actually, one that totally reflects light is also considered a black body, but it's on the other end of the spectrum. So he heated the black body, and it produced no light at first. But then when we come to a temperature which goes beyond 750 degrees centigrade, then we have a red glow of the iron, and when we do a spectrum, then we have a continuous spectrum. So something like a rainbow spectrum. And when you continue heating, then eventually go from a red to a yellow to a white glow, and that's the hottest. So beyond that, when we take a spectrum of this, we will get a line spectrum. And this is so interesting because the line spectrum tells us that the energy is quantized. That means we have distinct energy levels. And this was the revolutionary result of Planck's experiment. Goodbye, and I see you next time.